Okay, this video is going to look at the ILPAC organic chemistry pre-test. So this pack on the pre-test, I've attached a copy of it below if you don't have your own, but we'll just go for each question. So the first one, benzene and cyclohexene react with hydrogen in the presence of a catalyst according to the following reactions, and we get benzene, which is C6H6. And it's quite often drawn like this. There's other ways we draw it as well. In the diagram it's drawn like that, and they've compared this to cyclohexene. So this is a 6-carbon ring, and it appears like it's got 3 double bonds. This is a 6-carbon ring that's just got 1 double bond, and the enthalpy for the reaction here is minus 120 kilojoules per mole. So to turn this into cyclohexane, I'll give myself enough space, but just cyclohexane is 120 kilojoules per mole. To turn this into cyclohexane, which you'd imagine is 3 times more than this, because it's doing 3 bonds instead of just 1, is actually a lot lower. That's minus 208 kilojoules per mole. So the question asks, why does this happen? How can we account for this? And this is because although we've drawn benzene in this structure with these double bonds, they're not quite double bonds in the same way these are. Instead, in this one, we'll have that pi orbital overlap to form a pi bond. In this one, a similar thing happens, but they all go into the center. So we get all 6 electrons overlapping into the center to make kind of a central area of delocalized electrons, and this increases the stability. So we get, because this isn't quite the same bond here, this pi bond forming from a double bond is different from this electron dense region forming in a benzene ring, then we get different values here. So into A, suggest explanations for the following points: that as alkanes get bigger, their boiling point increases. So we take CH4, C2H6, and C3H8. So we've got here methane, ethane, and propane, and we want to know why do the boiling points increase? And that's purely to do with the number of intermolecular forces increasing. So there's no dipoles or anything like that in them. So they're all held together by induced dipole forces, probably London dispersion forces, it's a common term for it at the moment. And as you go along, the London dispersion forces increase because the number of electrons increases. Here we've got 10 electrons, here we've got 18 electrons, 26 electrons. Yeah, it's going up there each time. That makes sense. So yeah, as we're going along, we're getting more electrons, so the London dispersion forces get stronger. In B, organic compounds are usually more volatile than and have lower melting point than inorganic compounds. Inorganic compounds form into inorganic lattices, so strong lattices, whereas organic compounds, they form into simple covalent. Simple covalent are just held together by these weak intermolecular forces, so they're easier to get to melt or boil, so more volatile, which just means easier to boil. Classify the following compounds as saturated or unsaturated. So what we're looking for is double bonds. If it's got a double bond, it is unsaturated. If it hasn't got a double bond, then it's saturated. So 3A, we've got propane there. That is saturated with no double bond. Oh, a triple bond as well could be saturated, sorry, unsaturated. So here, and this one, we've got a triple bond there, so that is unsaturated. Then C, we've got a double bond up in that top right hand side. So C is unsaturated. D, we could work out we've got 2 carbons, 4 hydrogens. So we must have a double bond here. Each carbon needs 4 bonds in order to get nice and stable. So if it's just a single bond, it's only got 3. So it's going to have a 4th. So that is unsaturated. And then the final one, C4, H10, 5, 6, 7, 8, 9, 10. So no space for a double bond at all. So that's saturated. And then finally, we're going to look at whether compounds are, what shape compounds have. So if we start with ammonia, NH3. Nitrogen, group 5, so 5 electrons in its outer shell, and then bonding with 3 hydrogens, covalent bonds, so that's our NH3, so 3 bonded pairs and 1 lone pair make this look like this shape, which is trigonal pyramidal. So A, ammonia is trigonal pyramidal because it looks like a triangle pyramid. B, carbon dioxide. We've got a carbon. We're going to have a double bond with an oxygen this way, and a double bond with an oxygen this way, plus the spare electrons there. So this is carbon dioxide, looks like that, and that is a nice and straight line, so that's going to be linear. C, methane, classic methane. Carbon with 4 hydrogens around. Carbon's in group 4, so all 4 electrons from the carbon are in covalent bonds with the hydrogens, which gives us this caltrop shape, so that's tetrahedral. The ammonium ion, NH4+. So we saw ammonia earlier, had nitrogen with 5 electrons and 3 hydrogens around. Now the ammonium ion takes a 4th hydrogen, but a hydrogen ion gets added this time to make our ammonium now an ion. Overall it's got 1 positive charge. It's got 4 bonded pairs, no lone pairs now, so it looks just like methane did a sec ago. So that is tetrahedral and boron trifluoride. Not one you'll often see in organic chemistry, but it's just a boron that's not going to follow the octet rule here, rather annoyingly. So you either know this one or you don't. And so we get boron not following the octet rule. It's in group 3, so it forms 3 covalent bonds. And this is boron trifluoride. It's one you just either know about or you don't. I think it's the only example people know of trigonal planar, because it's 3 bonded pairs, no lone pairs. So it appears only ever in these sort of questions. Is there a question 5? No, that is the pre-test for the ILPAC.